Next up, we have Dino and Christina from Facebook.
Thanks, Jeremy. Hi, everyone. We're here from London, and we'll be speaking about Scribe. Scribe is a system that's been around for over a decade. It started out as a way to collect a bunch of application logs and kind of bundle them and store them in network storage. Over the years, the purpose of the system has evolved a lot, so has its scale. And as part of that, it has had to have been rewritten and re-architected multiple times. This is a phenomenon I'm sure many people will have encountered as well, so hopefully some of the lessons we've learned will be useful to all of you. In terms of what we're going to cover, we're going to start out just by quickly going over the system as a whole, a bit of an overview. And then we're going to take a look at two aspects of observability, one around kind of monitoring traffic as a whole, and the other one around our specific kind of tracing that we do for Scribe.
So what exactly is Scribe? It is a distributed transport system which is used to aggregate and transport log messages from one end to the other all across the Facebook infrastructure. So it was designed and recently re-architectured to be very simple to interact with. So it exposes a straightforward API for customers to write and read data to it. So in order to use it, you can use either our producer-consumer libraries and call the APIs there, or our binaries, which are available on pretty much every machine inside Facebook. And here is an example of that. We would write data into a logical stream, which we call a category, and then read it once or multiple times at the other end, very similar to a pipe. OK, but what's challenging about building and maintaining the system is the scale at which it operates. At any given point in time, it might ingest up to 2.5 terabytes per second and read up to 3 times more. So of course, we aggregate this data over hundreds of thousands of categories, all internal to Facebook. So the daily pattern may vary a lot, as you see it here. So our infrastructure needs to handle automatically this increase and decrease in traffic during peak times without any other maintainability operations.
So now that we've seen basically what Scribe does, let's take a look at the kind of landscape in which we operate in. A lot of what flows through the pipes will start off as something familiar, like a click, an impression, one of the products, perhaps a service event from one of the servers, a log, perhaps a feature used to train some machine learning model somewhere. And that gets written to Scribe. And it gets written to a category, as Christina mentioned earlier. Throughout the course of its kind of lifetime, the messages may get windowed, joined, aggregated using some of our real-time services like Puma or Stylus, which you may have heard of. They ultimately get written back into other Scribe categories, where they then make their way into more permanent and more durable storage systems like a data warehouse or something like real-time like Scuba, for which there will be a talk right after this, perhaps a key value store, an index, or some kind of aggregation. Popping the hood and taking a look at how things look on the inside, a message starts its life in a so-called producer. This is either a library or that can be linked in to somebody's binary, or a convenience binary that we provide. These payloads are essentially, they consist of a category and a message, as Christina mentioned earlier. And the first hop is from the producer, the message makes its way to something called Scribe-D. Scribe-D runs everywhere and constitutes the first hop on this write path. And that's where messages get batched for efficiency and then forwarded to something called the write service. The write service is just a stateless set of servers running. And the purpose of the write service is to take these messages, figure out in which one of the many storage clusters it will get stored. So every message ends up being stored in one of the many storage clusters run across the world. And because the payloads are very heterogeneous and we need to be able to find them again, every such cluster has a periodic job which kind of is in charge of figuring out which messages are present and advertising this fact in our internal service discovery system that is a shared bit of infrastructure available at Facebook. Meanwhile, on the consumer side, somebody might decide, an application somewhere may decide, oh, I would like to read the content of this category, at which point, again, either a library or a convenience binary will contact something called the read service. The read service, in turn, will take a look, consult this aforementioned service discovery, and figure out which clusters to contact. We'll open up connections, start streaming messages from those clusters, assemble them into a single stream, and deliver them to the consumer. And all this is run as a service internally, so other teams at Facebook don't need to run this infrastructure themselves. They just use it. I mentioned this briefly. These storage clusters, they run something called log device. Log device is a distributed storage system. And unlike some other storage systems you may be familiar with, rather than, say, a file, the fundamental primitive of log device is the log. And so the data itself is stored in an inherently sequential manner, mostly like append only. And given that we're in the business of moving streams of data around, this abstraction is very convenient for us. Log device itself is open source, so if you're interested in taking a look, go check out logdevice.io. So to recap the properties of Scribe, to kind of place it on the spectrum of trade-offs, the first thing to note is the messages that flow through the system are considered opaque. So Scribe will make no effort to try and understand what exactly is flowing through the system. It's more like bytes in, bytes out. Secondly, Scribe scales horizontally. So as, say, the throughput for a category increases, the system will automatically provision more space in the storage clusters and more servers as necessary in order to accommodate the traffic. Perhaps surprisingly, Scribe is slightly lossy. So if you remember the diagram we were seeing from the data plane, there are points in time where the only copy of a message in the system resides in memory of a single machine as it's being forwarded. And when running things at scale, machines will fail from time to time, which means that occasionally a message will get lost. Then with these kind of transport systems, you may wonder, how long does it take for the message to go from one end of the pipe to the other? Most of the time, this is in the seconds. Occasionally, this goes up to minutes. And perhaps philosophically, we consider Scribe a transport system rather than a storage system. So all data is considered ephemeral and kind of in transit, and the retention can go up to days.
So one of the most important observability metrics that we need at any given point in time is the throughput that goes into each one of the logical streams. It is critical to have a reliable view of the write and read traffic that flows through the system in order to isolate faults or assess Scribe's health. So this is kind of the primary signal that shows us that the infrastructure is working correctly. This is even more critical as we have other systems that depend on the data we collect here, like the demand control system inside Scribe, or other customer pipelines or alerting that could be embedding this data. So to give more details on how we use it, apart from the monitoring use cases, the demand control system is basically a service, an independent service, which allows us to allocate a quota to each of the customers, which they can use over as many categories as they want, and then allows us to blacklist certain streams in order to protect ourselves from being flooded. So we would compare the quota to the throughput we get, and then under specific conditions, we would blacklist categories as a means of protection. OK, but how does this work? The central piece is a rate monitoring job that runs every minute. It polls every cluster of the underlying distributed storage, so it gets the counters directly from the log device clusters. It aggregates these counters and then writes them to one of our internal time series storage inside Facebook, where it can be later queried by other consumers. So this needs to happen fast and reliable and account for all the millions of machines that send data to infrastructure. So now that we've seen how we traditionally build a monitoring system, what's challenging about this is the point that we run it at scale, and here we need to account for a different class of problems. So polling many machines with RPCs that can fail needs special care. We need to account for failure zones, either machines being unresponsive or data centers going down. And then we need to make sure that we handle correctly the aggregation of the shard data. Another point would be that since not all data compresses equally well, we need to make sure that we publish both the compressed and uncompressed metrics. So this is especially important for the demand control system, where we need to account for customers that send better compressible data. But again, the most important property of the system needs to be reliability. And here's a case in which when publishing took too long for one of the data set, so we actually attributed the traffic to the next minute. We saw this as a huge drop and an increase in throughput traffic, which we consider valid because we were thinking that someone was flooding us. So then we blacklisted a lot of important categories for customers. But in the end, it proved out that we had an induced latency which kept over-accumulating and resulting in this series of unfortunate events. So it's actually a thin line between a false positive and a real malfunctioning of the system, and we need to assess that correctly.
So now that we've seen how important it is to maintain an aggregate view of the traffic entering and leaving the system, the next thing we'd like to cover is our own kind of variant of tracing. And as you may kind of expect, tracing, or what we call tracing in this context, is about following the path a message takes through the system. This is useful for a variety of things. So for instance, let's say you're trying to troubleshoot something going wrong, being able to find an instance of this problem and figuring out what is happening in the system is very useful for debugging. What this also gives you is these individual traces can then be aggregated back up into an overall view with the property that as you see like anomalies or issues, you can kind of dive into the individual traces, which is quite nice. And lastly, one thing that traces also give us is a way of assessing how our customers are actually using the system. This can be useful to gauge where to invest engineering effort and which features to build, etc. So the idea for us behind the tracing is to take a subset of messages and give them a trace ID. So why a subset? Given the sheer number of messages that are flowing through Scribe at any point in time, it would be unreasonable to try and trace everything. So we sample the messages, and as you can see here on the right, we attach an optional trace ID. Now, whenever any component in Scribe sees a traced message, it essentially emits an event, and this event gets funneled into a central place where the events for all these kind of messages get joined together based on their trace ID and form sessions. So more schematically, here at the top we see the data plane as the messages get passed through. And as the various components on the write and read paths see messages that are traced, they emit these events. These events get sent to a central joiner. They get joined into sessions and stored in a key value store, which again is a shared and available bit of infrastructure inside Facebook. At the bottom, the last component of this is the processor, and the processor looks at these sessions, scans them all, and tries to make some kind of inference and deduce things from these sessions. So this may sound a bit vague, so let's take a look at an example of what we could do with tracing in our context. As I mentioned earlier, Scribe is a slightly lossy system, so at any point in time, like it is meaningful to wonder, like, okay, how much are we currently losing in order to be able to monitor that? So on the right here, we see an example of sessions as produced by the joiner. Each row corresponds to the path taken by one message through the system. And if you recall from the right path diagram, the hop that is responsible for persisting a message in log device is the write service hop. So essentially, loss basically manifests as a session where the write service hop is missing, right? So here you can see that as an example. If the write service hop is missing, it stands to reason that the message was lost. Now, this begs an interesting question. Is like, when do you actually check these sessions, and when do you try and assess whether this hop is missing, right? If you check too early, then the hop might just not have made it there yet, right? You may end up declaring a message lost, even though this write service hop is still on its way. So you end up with like a false positive. Perhaps more subtly, if you check too late, you will get a much more accurate view of whether or not something got lost, which is good. However, if the whole point of the exercise is to be able to monitor the system and to react quickly to problems or other issues, then you may end up waiting too long and compromising your ability to respond quickly enough. So the solution the pragmatic solution we've gone for in this instance is some variant of why not both. We basically evaluate these sessions multiple times at multiple intervals after they get created. For instance, at 5 minutes and then again at 1 hour, and use the results for different purposes. So now that we've seen some of the challenges that we've faced and how we've approached them, one takeaway here is that even things that conceptually sound embarrassingly simple get quite difficult at scale. So all the way from just even like measuring how much traffic is entering and leaving the system, to the fact that you can't just trace everything and you need to figure out how to like sample it correctly. We even have a third system that does something similar in order to observe Scribe that we didn't have time to go into here, but we can come find us later if you're interested. So basically, simple things can get difficult. And the second one is that in many kind of systems I've worked with in the past, the kind of common understanding was that you kind of, in order to observe the system, you set up a bunch of instrumentation and you kind of scrape the relevant binaries and you use that to figure out what's going on. But here, particularly with our tracing system, this is an instance where we've actually derived value from building an entire dedicated separate system with the sole purpose of monitoring the main system. So turns out occasionally that's a useful thing to do.
We're also exploring future work at the moment. As Dean was mentioning, Scribe is agnostic of the content of the messages, but we're exploring the idea of adding schema awareness to it, so that customers like maybe ML workloads that send structured data could select filters and only get dimensions of the data that are of interest for them. So that's the first step into kind of making Scribe a smart pipe. Another thing would be that since we have a high read amplification, I was mentioning that we might read up to 3 times more than we write, and a large portion of the traffic are reads. We're working on a project to adding caching to the read service, so we can improve performance of this operation in this way. On a constant basis, we're also revisiting our SLAs. So Scribe is lossy, but we're looking into kind of getting better delivery guarantees and looking into the trade-offs of what we could do to improve the loss percentage in this way.
All very interesting challenges. Luckily, we're not doing all of this alone. And now we've got some time to take a few questions.
Thank you, Dino and Christina. Questions for our Scribe friends? I promise I'll look to the sides.
Hi. I believe you mentioned somewhere like, you use this system to monitor anomalies. So does it take care of things like slow sessions? If I'm a user using Facebook and then like things are loading extremely slowly, as one of the speakers in the morning was saying, Would this system be able to help you out to point that out? If so, can you walk me through a sequence of steps at a very high level? Like, does it keep track of how long each thread or each function is doing? And then how do you get that information? How do you see it? And then, like, does it raise an alert or alarm or whatever else so that someone can go and fix it?
So ultimately, the systems we described here their main purpose is to monitor Scribe itself. So we will be interested in things like how long will it take a message in Scribe to go from like one end to the other, or whether or not it gets lost. In terms of basically using this for purposes of like specific products or like other applications, it's basically whatever the internal teams make of it, right? Like the system is available and can be used, but I think that there are too many different applications to go into right now. I mean, we can chat later as well.
Yeah, so we use it for alerting, but only inside our team, not for other products.
Thank you. I think we have another question right here. Yeah, you. On the third row. Second one in. Oh, sorry. We have. You're next. We'll do that. Do you and then you.
Okay. What can you tell me? What is it that's so special about Scribe that it can't use? I'm assuming Facebook has like a company-wide system for metrics and for tracing that we just heard about. So what is it about Scribe that makes it unable to use those systems? And how hard is it to generalize those systems so that you guys can have a unified framework of tracing and metrics?
So in general, Scribe does use the common infrastructure where possible. So for instance, for most of our time series, we use the available time series kind of storage and monitoring infrastructure. The tracing setup is a bit special in the sense that it deviates from the traditional tracing model of trees of RPCs. And it's more about following the path a message takes through the system, which can be like circular and reentrant and a bunch of things. So I'm not aware of a system that does this out of the box, but if there is one, then please let us know.
Thanks for the question. One more right here.
Hey, thank you for the speak. I had a question about trace IDs. You showcased a schema that had one trace ID, but you also mentioned that there are different models like circular reentrant. Is there a good rule of thumb when you want to regenerate them, or do you persist trace ID through all systems from beginning to the end? Does this make sense?
So if I understand the question, was it around how the trace ID is propagated through in order to allow our tracing?
Exactly.
So basically, the messages themselves, even though we don't look at the message of the payloads of the messages, they are embedded in a bit of structure that is used to forward them and to like. So as a message makes its way through the system, we will store metadata about it and remember like how many times things were retried or other properties. And the trace ID is essentially just attached to that bit of information such that whenever a component sees a message, it can easily check, is there a trace ID here and should I be emitting an event?
Thanks. One more time for one more question. Anybody on this side of the room? Okay. Thank you very much, Dino and Christina.
Thank you.
Here.